Hi everybody, today we're going to be looking at energy transformations. So far we've looked at different forms of energy. We've also looked at how we can calculate gravitational potential energy, kinetic energy, and work. So today we're going to be looking at what happens when energy changes from one form into another. So we started by looking at this skate park applet. That's a really good example to show you what happens with energy during transformations. So you can see here we've got a skater moving up and down on both sides of a ramp. And we have a little graph over here at the side demonstrating the amount of total energy, thermal, gravitational potential, and kinetic energy. And you can see here that as the skater goes up at the height of the top of the ramp, the gravitational potential energy is very, very high and equal to the total. So all the energy is gravitational versus the situation at the bottom. I'll just try to freeze it here, where pretty well all of the energy is in the form of kinetic energy, movement, and it goes back and forth without a change in total energy. Now things we can do are we can maybe add a little bit of friction. So as we add a little bit of friction, add a bit in here, you can see that as the skater's moving, especially towards the bottom of the ramp, the amount of thermal energy goes up. And what's gradually happening is we have the same amount of total energy, but what's happening is the energy is now distributed, so it's lost in the form of heat or thermal energy. So this is about as high as the skater can go now, and you can see that it's a lot less than before, again, because the energy, a lot of the energy has been lost in the form of friction. And similarly at the bottom of the ramp, same situation is true, a lot of the kinetic energy is gone as well. So again, because of that loss. And eventually what's going to happen is the skater will gradually lose more and more and more energy and eventually come to a stop. And hopefully it's going to happen soon. And you see that all of the energy is eventually going to end up in the form of thermal. So again, the main idea here is that the total amount of energy remains constant. We say it's conserved while the energy can switch back and forth between different forms. And if we have not 100% transfer, the energy is lost in the form of heat or thermal energy. You see here the skater is actually stopping. So this is the handout that we have, and just a couple definitions here. So basically it's looking at what mechanical energy is. We'll talk about that in a bit. But the big things here is a little situation. We have a scenario where we've got a car, like a roller coaster, and we're going to keep track of the energy at different points. Now remember what we just saw, the total amount of energy is going to be constant. So what's going to happen here, it's going to keep track of the gravitational potential energy first, and then we're going to keep track of the kinetic energy. So we're going to assume at the top that we're not moving and all of the energy is in the form of 100% pure Eg. At the bottom here, we're going to have no Eg, so 0% Eg. 25 meters up, it's going to be about 25% Eg. And in the loop, it's going to be 75% Eg. And then the car comes down, and the Eg is going to go to 0. So it's going to be 0% Eg. Now, according to conservation of energy, the other energy is going to be Ek. So at the top, we have no Ek, it's all Eg. And at the bottom of the hill, all of the energy has now been transferred into Ek. The vehicle is going to be moving. Here, when we're 25 a hill, it's 25% the height of the original. The Ek is going to be 75%, and the Eg is 25. Here, we have 75% of the energy is Eg. The other 25 is going to be Ek. And at the bottom, all the energy ends up as Ek again. So you can see here that the total is always 100% energy. So what's happening is energy is transferring between the two different forms. Now the total energy, we're going to call it mechanical energy. So the total mechanical energy is constant in the system, and it's going to be composed of kinetic and gravitational, and it can change back and forth between the different forms. So I have here a little statement here. So law of conservation of energy. So in a closed system, the total energy is constant. Very important to remember that. Energy cannot be created or destroyed. All that can happen, it can change form from one to another during an energy transformation. So again, what happens is we have a total amount of energy conserved. So I can write down E total initial is going to the E total final. So the energy I have at the beginning is going to be the same as the energy at the end. What happens though, the proportion could change. So at the beginning, I could have maybe some EG initial, EK initial, and that's going to equal the sum of the EG final plus the EK final. Again, the energy is constant, it just switches back and forth. So at the beginning, in the roller coaster, we had 100% EG at the beginning. At the bottom, it was 100% EK. Okay, I think a great way to do this is to actually look at an example here. So this is a question of the Leviathan, the new coaster they have in Wonderland. And the first hill is 93.3 meters high. It's quite a large coaster. So we're going to draw a little sketch here to kind of figure out what's going on. So I know that the top of the hill, I'm going to have some EG, and the hill is 93.3 meters high. And I want to know what's the theoretical maximum speed or velocity at the bottom of the hill if there's no friction. So I want to know what the velocity is down here. In other words, we have to calculate the EK. So at the top, we're going to have 100% EG. At the bottom, it's going to be 100% EK. So a good way to do these problems is to look at what we have at the beginning, so the initial, and then look at the final, what you have at the end. So let's look at the initial. Now initially, remember, the other thing too is that my energy is going to remain constant. So I'm going to have my E initial. It's going to equal my E final. There's no difference between them. I'm going to start writing down some quantities that I have. So initially, I know I'm going to have a height, 93.3 meters. And I know my initial velocity is going to be 0. I'm not moving. Similarly, on this side, or the final side, I'm going to have a height of 0. I'm at the ground. And I'm going to calculate the final speed or velocity. I'm trying to calculate that. So what we know is at the beginning, all I have is EG. And that EG is going to be changed into EK. And we know the equations here. MGH initial is equal to 1/2 mv final velocity squared. So what happens here, interesting, is my mass is going to cancel. So write down a little bit here. So notice mass is a common variable, therefore cancels. This is not always true, but it's very handy in this case. So that's why we do not need a height. Therefore, do not require, a mass. That's what I meant to say. A mass of coaster. There we go. Okay, so let's plug our numbers in and see what we have. So 9.81 meters per second squared times my height, 93.3 meters, is equal to 1/2 VF squared. So I'm going to multiply both sides by 2, and we end up with 42.8 meters squared second squared, and we'll square root both sides, and we get 42.8 meters per second. And it looks like it's 3 significant digits, so we can jot this down. So therefore, the speed at the bottom of the hill is 42.8 meters per second. Remember, this is assuming that there's no friction associated with it. So we had 100% Eg changed to Ek. That's represented in my equation over here. Okay. Let's look at another example here. So this example, I've got a ball that's going to be going straight up with a velocity of 20 meters per second. I want to know how high it's going to go. So, little diagram. There's my baseball. And it's going to be thrown with an initial velocity of 20 meters per second. And I know it's going to have a velocity of 0 at maximum height. And I want to figure out what the maximum height is. And we're assuming that we're at ground level and we're throwing it. So what we have here is we've got Ek energy being transformed into Eg energy. So I'm going to write down my quantities that I know. So initially, I know that my height is 0 on my ground level. My initial velocity is 20 meters per second. And at the end, I have my final height, which I'm trying to find. And I know my velocity is going to be 0 at that point. Speed is going to be 0. So what we know is this. I know the Eg is going to be changed into, or sorry, Ek. Let me fix this. Sorry about that. So the Ek is going to be changed into Eg at the end. And we gain some gravitational potential energy. We know my equations. 1/2 mv squared is mgh. And much like before, masses will cancel. So I'm going to have 1/2 20 meters per second squared is equal to 9.81 meters per second squared. And that's going to be times my height. So we rearrange a little bit, do a little bit of magical math, end up with 24 or 20.4 meters as my final height. Therefore, the ball will reach a maximum height of 20.4 meters. Again, 3 significant digits in this situation. Okay. Now, we have another one here. Now, something else I want to point out. The mechanical energy isn't the only thing that's conserved. All the other energy forms can also be conserved, including work. So what we can do is we can go back up to the top, right here. Remember we had the total initial is equal to the total final? I can also add work in here. So the total work and mechanical energy are conserved. That's going to come in useful in the next situation. So let's take a look at what we have here. So I've got the vortex. It's a suspended roller coaster that drops 26 meters from Wonder Mountain. And the trains swing just above the water before coming to a stop over a distance of 5 meters. What braking force is required to stop the train? So what's happening here is I'm going to be falling down the mountain. So I'm going to start with Eg at the top. It's going to change into Ek at the bottom of the first hill. And then it looks like we have applied force and there's a distance. So that probably tells us it's going to be some kind of work. So I'm going to start up with Eg and going to end up with work energy. Remember, energy of work is change in energy is really work. So I know, write down some givens here. My initial height is 26. I don't have any velocity at the top. I know at the bottom I have a height of 0. My force applied is unknown. And I have a change in displacement of 5 meters. And the other thing we know is at the end, I'm not going to have any speed. All the energy is going to be in the form of work energy. So I know the final velocity is also 0. I'm coming to a stop, if you remember. So let's write down my energy equation. The initial final, and let's see what we have here. So again, initial height is 26, initial velocity 0, and final height is 0, final velocity is 0, but I do know that there's a force applied, and that the force is acting over a distance of 5 meters. So what's happening here is I've got my EG initial being changed into work final. So again, look for your little key ideas, key variables. So work would have force associated with it. So I've got my equation, mg initial, is going to be equal to force applied times my distance. So what we have here, we've got 4,200 kilograms is my mass. Remember, it's a roller coaster, so it's quite heavy. 9.1 meters per second squared. My initial height was 26 meters. And that's going to equal to my force applied times 5 meters. So I'm going to clean up a little bit. Oh, one thing I do want to point out, the masses do not cancel. I don't have a mass on this side, so we have to maintain it here. So we're going to get a value of 107.1252 over 5. That's going to equal to my applied force. So my applied force is going to be 214,250 newtons. Again, it's quite large because we're stopping a roller coaster after all. So therefore, the braking force required to stop the coaster is, and with significant digits, because it's 26 meters, 2, it'd be 2 significant digits, so 210,000 newtons, and it's going to be backwards, opposing the motion. So that's important as well. So that's it. I just do want to point out, so look for your key variables. It's going to go back up to the top. So in this situation, force, think of applied force with work. EG has height associated with it. EK is going to have some kind of velocity. It gives you some clues as to what's going on. Okay, well, let's look at one question here. We've got a combination of energy associated with it. So what I have here, I've got another roller coaster question. So it's the Mind Buster. Again, 26 meters high. And the mass of the coaster is 2,750. I want to know how fast is it going 15 meters down the first hill. So let's draw a little sketch. So my sketch looks like this. So at the top, I'm going to have my height, 26 meters. I'm going to have EG. Now, falling 15 meters, my height's not 15. It's 26 minus 15 meters, which is going to be 11 meters. So in other words, I want to know how fast I'm going at that point. So here, I'm going to have some EG, but because I haven't fallen all the way, so that's why I have the EG, and because I've fallen partially, I also have some velocity here. And I'm going to figure that out. So I also know that I've got EK final. I've got both forms of energy. So here what happens is I'm going to have my EG initial being transformed into some EK with a little bit of leftover EG as a result. So let's write down our quantities here. So initial, final. So again, initially, my height is 26 meters. Final height is going to be 11 meters above the ground. My initial velocity is 0. Final velocity here is what I'm trying to find. Okay, put some numbers in here. So mgh initial is 1/2 mv final squared plus mgh final. So it's going to be quite large. Lucky for us, mass is due here. So I'll make it a little bit easier. So I got 9.81 meters per second squared times my height is equal to 1/2 VF squared plus 9.81 meters per second squared times my final height of 11 meters. So when we do this, I'm going to get 25,506 minus, over here looks like 72. Nope, I think I made a mistake here. Erase this. A little boo-boo here. Sorry about that, folks. So it's going to be 25.6 is equal to 107.9 plus 1/2 VF squared. So I'm going to have in the end 17.2 is equal to VF. So therefore, the final velocity after falling 15 meters is 17 meters per second. And that's it. So just again, what's showing you here is that I can have two forms of energy present at the same time in a particular location. So again, drawing a little sketch will make life a little bit easier for you. So for the other answers, just check the answers that are posted on the website. And hopefully this helped you a little bit in terms of understanding what's happening with the conservation of energy questions. Take care.